in taking images of crystals, I think probably most of us work closer to focus than people do when they're taking images of single particles, just because we use different methods for finding the crystals. We look at usually the diffraction pattern of the image and sort of either scan over an optical diffractometer or computer real-time Fourier transform. We look for diffraction spots in the transform rather than looking for single particles. So we don't have the same need for that low frequency contrast, I would say. And in any case, we often don't work with the lowest orders of the diffraction data. And so I think maybe there's not quite the same need for the phase contrast. But we still have needs that are at least as great as everybody else for things like electron detection. And that's the focus of this talk here. So the electron detector, as you see, sits somewhere under the column of the microscope. And for many of us, that's still photographic film. And I think, especially in the context of electron crystallography, there are probably more people still using film than CCDs. But the CCD is really the other up-and-coming recording system that we would all love to have instead of having to deal with film and all the delay and processing it involves. So what I wanted to talk about is sort of to answer some of the questions that have come up here. What are the criteria for judging the performance of a camera, whether it be film or CCD or something newer? So the characteristics we've talked about are the modulation transfer function, and it may not be obvious to everybody that this is a function of spatial frequency that just is the ratio of the output contrast divided by the input contrast. So it represents whatever degradation occurs in the camera system of the contrast at a particular spatial frequency. Well, it's a function for all spatial frequencies. The DQE is a little more complicated because it includes the noise level. It doesn't really address the modulation transfer function directly. The definition is that the DQE is equal to the output signal to noise ratio squared divided by the input signal to noise ratio squared. I must have this backwards. Since the DQE is always less than 1, and the output signal to noise ratio is always lower, signal to noise ratio decreases, of course, so this is correct. But it's the signal to noise ratio that this addresses. And originally this was conceived as just one measure for a system. It was not a function of spatial frequency, but over the last roughly 10 years, I think at least in the context of imaging systems, cameras and such, and more people have begun to treat this as a function of spatial frequency. And as such, it does depend strongly on the MTF. In fact, you can write an equation where the DQE is defined by the MTF divided by the dose, perhaps with another factor in there, but the dose actually, in the context of what we do mostly, gives you the signal to noise ratio in a system that's shock noise limited, where the noise is proportional to the square root of the exposure. Of course, the number of pixels is a critical factor in determining the value or figure of merit or desirability of any sort of image recording system, and perhaps more in the context of crystallography than in other applications. But I just wanted to review the structure of these things, photographic film and the CCD. You've seen a picture of CCDs a number of times here already, but just to refresh your memory, in case you haven't looked carefully at your film, there's this is the cross section, not the top view. Okay, so there's a fairly thick plastic layer that is most of the bulk of the film. That's just a carrier, On top of that, there's a thin layer of what's called the emulsion. That's a lot of small silver halide grains embedded in some kind of a gel. The silver grains in the films that we use are very small. They're perhaps a fraction of a micron or less than about a micron in size, and they're fairly densely backed in there. On top of that, there is usually some kind of a very thin protective layer. The protective layer here is thin enough and a light enough weight material that it doesn't really have much influence on the electrons. In fact, this plastic support doesn't really stop all of the electrons, especially at 300 keV, say. A lot of electrons go straight through here, or maybe it's some of the X-rays produced in the process of going through, of the electrons stopping there, but I think mainly it's electrons going all the way through the emulsion. In any case, some of the electrons, or probably all of the electrons, interact with some of the silver halide little microcrystals in here, the grains, and make them developable in the chemicals of the developer. Backscattering, I think you have noticed, is a significant problem in affecting the performance of various detectors. That's probably not a very significant factor in film. This material of the plastic support is light enough that it doesn't produce much backscattering. So once an electron goes through the protective layer, through the emulsion, it probably just goes shooting on through the rest of the film. The density in the emulsion is significantly higher than the density in here. That's the mass density. So this is the region where most of the energy would be absorbed. But probably at 300 keV certainly, and probably also at 100 keV, not much of the electron energy is captured in the emulsion here. What that means is at 300 keV, fewer electrons, or less energy is actually deposited in here. Fewer grains are made developable. And the speed of the film, which is the optical density that you get for a certain number of electrons, goes down by something like a factor of 2 as you go from 100 keV electrons to 300 or 400 keV electrons. The optical density here as a function of exposure is not a very linear function. In the low optical density range, it's a pretty good approximation of a linear behavior. Although there is an offset in optical density that you get with no exposure. That's the fog level of the film. So some of these grains are just naturally developable for various reasons that nobody's been able to completely control. So even with no exposure, there is a certain level of density in here. And as you get higher and higher exposure, the OD sort of plateaus and reaches a maximum level that's determined by the maximum amount of silver that's put into or silver halide that's put into the emulsion. And with the films that we use, the Kodak SO163 film, that's pretty opaque. And how much silver there is determines how good an approximation this is to linear at the low density range. But still, if you're doing something like electron diffraction, where the range of exposures covers a wide range here, the response is going to be very nonlinear. If you're recording images of a cryo sample where the range of exposure is very narrow, then it's probably a pretty good approximation to a linear detector. So another picture of a CCD. Here there's a scintillator that is what absorbs electrons, or absorbs electron energy and converts that energy to light. And that's channeled through fiber optics, usually down to the CCD level. And just a couple of characteristics that by now I expect you're pretty familiar with, that the scintillator has to be fairly thin in order to avoid scattering of electrons and photons within the scintillator. But what that means is that a lot of electrons also go through the cinder layer, just like they go through the emulsion of the film. So in many cases, only a small fraction of the electron energy is actually captured in the scintillator. There's another factor that has to do with the conversion of the light to signal in the CCD. That light is reconverted back again into electrons that are stored in wells, or the pixels of the CCD. And that conversion of photons to electrons, referred to as the quantum efficiency of the CCD, is significantly below 1. It's possible to adjust that some, but it's a factor that does vary from one type of CCD to another. One of the nicest things about CCDs is that they don't have much of a signal corresponding to the fog level of film. They do have a little bit, but it's almost something we can ignore in the context of exposures that we use here. They also have a very wide dynamic range. I don't know what we would say the dynamic range is for film. It's something like a factor of 10 or maybe 100 if you do some corrections. But typically it's a factor of, say, 10 to the 4th for CCD. That's not enough to cover the whole range of intensities that you find in an electron diffraction pattern, especially if you include the unscattered beam and the area around it, but it's vastly better than with film. So, enough of structure. I was hoping this might come out a little bit differently than it does here. This is originally a very high resolution pattern of spokes where there's really 100% contrast between the dark bars and the white bars, all the way into what you see here as a little white dot in the center. This was a fairly expensive test pattern. And so it had, the original version of it had little bars that were about a micron across, right in toward the center. This was actually digitized on a maybe our Nikon scanning densitometer.
It's perfect.
Well, it's not, because even up here, I can see that the contrast disappears about here. And I know that the signal goes into here. But standing right here, I can see that there are funny sort of what we call aliasing effects where the image is not really well preserved in this region out here, just before the contrast really disappears. And I thought maybe that would show up a little bit better. We don't have control over the focus of the projector, do we? Okay, so we'll just ignore that. If we could defocus this, we would see all sorts of bizarre effects as the contrast would vary, would reverse in certain zones here. And you do all sorts of strange things that are similar to the contrast reversals that you get in the electron microscope. That wasn't the point. The point was, first off, that the contrast of this image of a perfect test pattern isn't very good in the high resolution range. That's an effect of the modulation transfer function of the digitizing system and possibly the projector here. That's the sort of thing we face anytime we record an image and then try to digitize it, say. Especially digitizing it has its own modulation transfer function, which is in general, in the ideal condition, represented by a sync function shown here. The Nyquist frequency that has come up in conversation generally represents the limit of a reliable detectability of a digitized image. There's a famous theorem by Shannon and Whittaker that says let me not go into that right now. That's just kind of a nuisance. But this curve here is still kind of interesting. At this point, twice the Nyquist frequency corresponds to the frequency, the spatial frequency, where there is a full cycle, so a plus and a minus lobe of contrast variation in a signal within a single pixel. And at that frequency, the plus and the minus cancel each other exactly. No matter where you start, if it goes from here, up and down to here, or if it starts here, down and up to here, that cancels completely. So at this frequency here, twice the Nyquist frequency, you can get no contrast in the digitized image. At the Nyquist frequency, where you have 1 pixel per cycle of the signal, so the signal is the frequency that corresponds to the spacing between pixels. Sometimes the pixels and the signal will be right in phase, so there will be a pixel here right under a positive lobe of the signal, another pixel under the negative lobe, and so on. There you'll get pretty good contrast, but other times you'll have pixels that are shifted half, and you get no contrast whatever. So the average contrast is down to about 60%. If your signal has spatial frequencies that are higher than twice the Nyquist frequency, those actually can be recorded, but they'll have reverse contrast.
So can you record them? How can you distinguish between that and the mirrored and lower resolution?
Well, there's an interesting point.
It's a licensing thing.
You really can't. So, so if you have frequency components up in this range here, they will appear when you take the Fourier transform of your digitized image superimposed on the rest of the Fourier transform. And that often happens in real life when there's a lot of noise in the signal at high frequencies that gets sort of folded back, or as we say, aliased back into the part of the signal that you're actually using. So we try to arrange that there is not signal out past the Nyquist frequency, but of course that's not something you can really ever arrange in real life.
So looking at the Film microscope, that happened in Basel. They had a very high resolution crystal and were scanning with pixel sampling level that was too large. And so the Fourier transformation showed the fraction pattern to the edge, and they were bouncing back into the image.
Right.
Yeah.
Right.
So
Yeah, just as it can also happen if your image is gold lattice. So you
Yes.
then you may have spots outside the Nyquist frequency, and they are folded back into it.
So this graph here is tightly compressed compared to other MTF graphs you've seen, which show the MTF of the system in this range here, up to the Nyquist frequency. And most of the systems that have been talked about have an MTF of their own. The whole system MTF drops to about 0 here, so that this aliasing is not an issue. But it is an issue for something like film digitizing, where the response of the system might be a lot better, or if one could develop a CCD type system where the MTF was really good at very high frequencies. Just something to watch out for, but keep that in mind. So, when we have an image on film, I'm just curious, who is collecting images of crystals on film these days or these years? Okay, and who wishes there were? Oh no, who's collecting on CCDs? Oh, okay. So in the old days, everybody collected on film. And we used to digitize the film, and those of us who still do collect probably still, you'll have to tell me maybe, or somebody, digitized the film so that the target resolution corresponded to just about the Nyquist resolution. We always used to use probably, I guess, a 10 micron aperture on our old PDS densitometer for images recorded at 60,000 magnification. I think that corresponded to 1.6 angstroms, so that our resolution limit was 3.2 angstroms. It was a little bit more than that, maybe 3.4. But that actually was our target resolution at the time. And I'm not really sure, well, so this developed because Richard Henderson, I guess, had pointed out that at least in cases where you're limited by computing power, it's better to digitize the image right out to the Nyquist limit than to digitize so that you're just using a smaller fraction of the Nyquist limit, and therefore you're constrained to digitizing smaller areas of the crystal. Better to digitize the whole crystal with just enough resolution to get to the Nyquist limit. The habit seems to have developed, though, with people working on single particle projects, to digitize so that they're using a very small fraction of the spatial frequency available. Maybe to a third of the Nyquist frequency, I think sometimes even a fifth of the Nyquist. So if you're digitizing so that your target resolution is a third of the Nyquist frequency, you hardly care what's happening out at the Nyquist. If the MTF is 0, that's actually it's better, because then there's a guarantee that you will not get any of this noise aliased back onto your original image. So there are other reasons for doing that, which have to do with the fact that anytime you do an image interpolation or rotation or rescaling or something, there's another MTF that's a lot like the digitizing MTF that decreases the contrast, particularly near the Nyquist resolution. But that decreases both the signal and the noise, so I don't think that's a strong argument for really oversampling the image so that you have signal only out to a fraction of the Nyquist frequency. In any case, the biggest problem with digitizing so that you're using just a fraction of the spatial frequency, say to a third of the Nyquist frequency, is that then you can only digitize a third of the size of the array, or a ninth of the area that you could if you're using all the way out to the Nyquist limit. So this is the typical IQ plot. And there are many cases, this is from one of our tubular crystals. You can see the diffraction spots out to about 3.5 angstroms do go up pretty close to the limit here, which is the actual Nyquist frequency. And in many cases, they really do go just right out to the edge. So one could come up with reasons why that shouldn't be so good, but in practice, it really does work well. It has to do with the fact that the MTF of the film that we're using still has a finite value, even out at this highest level here. So these are measurements that we made quite a long time ago, scanning films of a regular pattern using a 5-micron aperture. So the spacing here corresponds to 10 microns. So that's 10 microns, 20 microns. So this is the level here that we would be reaching with our 10-micron aperture. So the MTF of the film at 10 microns is down to something like 30%. So see, the 50% limit that Bob's talking about is a little bit soft, but it's close to 50%. So film is really good. And in fact, film has the funny thing that it probably gets better at higher accelerating voltages, whereas the bad thing about CCDs is they get a lot worse. But how many pixels, how big an area would you really like to have? So you really would like to have, as Henning said, a crystal that's bigger than a micron, say a micron and a half. Then you could get sort of nice diffraction patterns. If you have a 5-micron crystal, you'll get much better diffraction. But with a micron or micron and a half, you can get pretty good electron diffraction. Of course, you can get images of much smaller crystals, but if you have crystals big enough to get diffraction, why not take an image of the whole crystal? The reason is that if you're digitizing to get 3 angstrom resolution, and therefore using pixels that are about an angstrom and a half, you need an array that's 10,000 pixels on edge. And 2DX doesn't even work with 8,000 pixels on edge, right?
Crashes at
There's
10,000.
something about, sorry?
It crashes at 10,000.
Yeah, so there's a lot of things that crash at 10,000. So in fact, we always used to digitize our tubulin images at sort of 4,000 to 6,000 pixels on edge, but that's because we also would go to lunch or go home for the night while we were running an unbending process, because Fourier transform of a 6,000 pixel array would take half an hour if we were using the computer all by ourselves, and maybe overnight if there was anybody else who was trying to do something. But the fact is that it would be nice if we could work with 10K images. 5K images are okay. We can do an awful lot with those. 4K images are good, which is nice because we have 4K CCDs available now. But the fact is that they don't often give us 4,000 real pixels. With film, of course, you can get 10,000 pixels on edge. You could digitize at 5 microns and get a lot more than that. We're digitizing typically at 6 1/3 microns. You end up with a file that's 225 megabytes in size. That was the size of our original hard drive when we first bought our own hard drive. We should all be striving for going way beyond what we can do right now, of course. So pixel sizes on CCDs. We were delighted when we could get to a 1K image size, 1,000 by 1,000 pixels. Most of us are pretty happy with 4K by 4K at this point. And in fact, that would be a good size for starting to work with high resolution crystals even. So, as I pointed out, with film, the resolution improves, but the sensitivity gets worse as you go from, say, 100 kb to 300 kb. With the CCD, both the resolution and sensitivity get worse. This says compatible with automated EM resolution. That is the CCD. Basically, you really need a CCD to do automated image collection, whether it's single particle, diffraction, crystals, whatever. You need a really high quality CCD camera. Just in passing, I would mention that the target exposures to the specimens that we typically work towards are on the order of 10 electrons per square angstrom. With a 1 angstrom pixel, that corresponds to 10 electrons per pixel, which is high compared to the noise level of a CCD, but not so high compared to the noise level of film, which is another reason that CCDs should in principle be better than film for recording images, possibly even single particle images.
So another question, the signal from the CCD is proportional to the intensity of the beam,
Yes.
which is proportional to the protein density, roughly. But of the sample. And on film, the optical density is proportional to the intensity of the beam.
Right.
But what the scanner gives you is a transmission, most scanners.
That's right. So you should convert the transmission to optical, to
you
keep
should,
your
but
optical
what
density
happens if
absolute.
you don't? If you just take your TIFF image and start processing, you get wrong amplitudes. Yeah, so because this logarithm is missing.
Right.
Is
So
that
that's a pretty good question. So in the case where you have very low contrast, you can approximate anything by some linear function, and the duration of a logarithm is pretty linear within a small range of exposure. So certainly a lot of people have done that, and I don't think they've run into trouble. So the critical thing in getting the critical factor you'd like to get out of your images is really the phases. And I don't think any misestimation of exposure is going to affect the phases at all. Chris showed a really beautiful movie of some of these Monte Carlo simulations of electrons scattering within a scintillator and then within the substrate below. And this is just a couple of examples that I pulled out of so much earlier where electrons scattering in a YAG scintillator that's sitting on fiber optics. So these are pretty good simulations. They're not meant to be the absolute true representation of what's happening in the real system, but they're a very good sort of qualitative description of what happens when you hit the YAG scintillator with 100 kV electrons, and they all stop in the first. I wish I knew this. I think this is 40 micron thickness. So. And I don't have the scale on this anymore. So let's say that this is 40 micron thickness. The electrons all stop within the first 20 microns, and they spread out something like 20 microns. At 200 kV, some of them actually get all the way through with that 40 microns of scintillator, and they spread out something that's comparable to 40 or more microns. At 300 kV, the electrons get really far down into the scintillator, even farther at 400 kV. And what also happens here is some of them travel a long distance in the scintillator and then come back up into the in the fiber optic substrate. Then they come back up into the scintillator and deposit a very large amount of energy, producing a lot of light a very long way from where they came in. So
I think your power came out, you're almost stepping on it, so I put it away.
Bob's fault.
Yep.
Okay.
So, Richard Henderson just gave a talk on the Bonn conference in Italy and showed data that I think you have collected with him with very low electron exposure. And then you tried to look at this and you saw something else, which was in half of the cases there were two spots. One sharp one and a bigger one for one electron. So the point spread function was a sharp entrance into the material, and then somewhere it came back up, and then had a bigger point.
Was this experimental, or
that was the new
metaphysics?
I think it probably was a simulation like this.
I think it was experimental. It was experimental.
Yeah.
I see.
So that's entirely possible. So look at single electron tracks. So each one of these simulations, I think, is a summary of about 20 electron tracks. If you look at a single track, you would almost always see a spot in the center here. And then occasionally you would see another spot where the electron came back into the center. Now that would be a bigger spot because the electron has much lower energy at that point. Of course, the energy deposited per distance traveled is going to be much greater. And the amount of light that it produces here could be a lot more than the amount of light it produces as it goes through the first time.
He also said, so the total integral of the intensity varied by a factor of 20 from one electron to the other.
That's a really big problem, and
That's shocking.
Glad you mentioned that. That is shocking. That was a surprise to me. The fact that, first off, that the electrons go through the scintillator. So say at 300 kV, almost all the electrons go through the scintillator. A few of them actually get scattered within the scintillator, and this one here goes sideways. This one here loses all of its energy in the scintillator, and that produces 300 kilovolts worth of light. That's a really bright signal for that one electron. There's another one here, I think is this one here, that only lasts 10 kV of energy. I'm making that up, but that's an example. So a lot of these lose on the order of 30 kV of energy in the scintillator. That's converted to light. But that number varies tremendously in these upper ranges here. This is a 40 micron scintillator. Nobody would use a scintillator that thick. 20 microns is probably more realistic. So the point here is that the amount of light produced per electron varies tremendously. And that's shown in this plot here, again from these simulations. But this, for example, the this sort of yellowish curve, 100 kV. So this peak here is the number of photons. So the number of photons, the number of scattering events, or the number of electrons. So this is the number of electrons that produce a certain amount of light on this axis here. So at 100 kV, almost all of the electrons produce this much light. So this much here. So about 4,000, whatever. Could be photons, could be units. With 200 kV electrons, most of the electrons produce about twice as much light. But if you look down here, there's a tail on this curve over here. A lot of them produce just a fraction of that amount. At 400 kV, almost none of them produce 400 kV worth of light, although a few do. So a few of them actually producing a really bright, intense spot. Most of them produce a small amount of light, but even in this range here, the variance in the number of photons per electron is really, really broad. So this is a noise source that had been appreciated in medical imaging, but I think people in electron microscopy were really slow to identify this as a limiting factor. That's a noise source in addition to shot noise that looks a lot like shot noise, but is not something that, like shot noise, would be limited or decreased by the MTF of the detector system. So this is noise in the detector. It's not noise coming into the detector that gets filtered or smoothed out by the detector.
Just a remark, I think in early paper by Dabaco and Hartmann and so on,
Yes.
they have similar curves.
That's right, in about 1990.
1990,
Right.
something like that.
And they had pointed it out, and I think it didn't resurface for 5 years or so. So anyway, from those Monte Carlo simulations, I came up with a graph of the approximate point spread function as a function, the size of the point spread function. So this is the size of the cloud of light that's produced by a bunch of electrons as a function of the accelerating voltage of the microscope. So at 100 kV, we're here sort of around 20 micron diameter. When we get up to 400 kV, we're up about a factor of 10. What that means is our resolution in the scintillator has gone down by about a factor of 10. That's going from 100 to 400 kV. Of course, if you go the other way down to 20 kV, the point spread function would be about a micron and a half. But who could get there? Film, on the other hand, I just, again, sort of made up this line here. The resolution certainly gets better as you go higher in accelerating voltage on the film. The reason is that at low voltage, suppose you went to such a low voltage that all of the electrons got stopped in the emulsion, there would be some kind of a cloud, scattering within the emulsion zone. At higher voltage, the electrons pretty much go straight through. You can see that in the simulations also. So the resolution actually gets a little bit better as you go to higher voltage in the film. I don't really know how much better. But this point spread function increase is one of the worst problems of using a CCD at high voltage. And of course, we all want to go to high voltage because everything else of the microscope gets better. The coherence gets better, the gun brightness gets better, the resistance to mechanical vibrations gets better, all the mathematical approximations we use in treating the image get better. Thinking about that finally drove me to the idea that if we slow the electrons down before they hit the scintillator, we would be able to use the microscope at high voltage, but get all the advantages of the camera at low voltage. So this is the project I've been working on for quite a bit of time, a decelerator CCD system that a number of people asked me about here. So I thought I'd talk just about a little bit about this. I guess I've gone over my time already. But kind of in the context of dealing with some of the parameters that are important in analyzing camera performance. Here we can actually vary the performance all over the map. So this is more clear diagram of how the system works, basically. There's a retarding electric field that the electrons see as they come out of the bottom of the microscope before they hit the CCD camera. So we have a commercial accelerator tube, just reversed to use as a decelerator. That's this section in here. The electron beam comes down through here. And all the stuff in red here is at some high potential, having all this at a voltage that might be 200 or 250 kV negative is what produces this field that slows the electrons down. So essentially, if the electrons enter here with 300 kV, they see a retarding field of 250, they'll hit the scintillator with just 50 kilovolts of energy. So the CCD chip itself sits down in the bottom of here, and the way we put this together, all of the camera electronics that normally sit in the box on top of the microscope console is packaged inside a little container that sits inside this tank here, all sitting at high voltage. So there's a sulfur hexafluoride at high pressure that's used as an insulating gas here. So this is a real high voltage, high pressure system that is used just to put the CCD at a voltage that gets sort of comparable to the voltage of the filament of the microscope. This is what it looks like. It sits in, this is the tank sitting under the knee hole of our JUL 3100. There's a 250 kV power supply and a transformer that adds the power to run all the electronics out there. There's fiber optic lines that take the signals out and send in the control lines and everything. So it's been a big and fun and interesting engineering project, but the fact is that it actually works. So here's some Fourier transforms of images of the beam stop. The beam stop is a fairly good sharp edge that is useful for defining the resolution of the system. And at 250 kV, you can see the beam stop Fourier transform goes right up about the edge of the Nyquist limit here. At 250, slowed down to 50 kilovolts, so 50 kV at the scintillator. You can see some of this aliasing that Henning talked about showing up. Sort of, it's essentially the continuation of this line up here that gets folded back over to here. So that represents what looks like a sort of moderate improvement in the resolution. That's an improvement in the modulation transfer function. And you sort of get a sense of that from line plots of the amplitudes along.
So the different KVs where you had sort of one main signal peak and then another one which was a scattering event, wasn't it? There was more events as you, scattered events as you went up in KV. So my question was really in that, with regards to that graphic in lens coupled systems or with the decelerating system, do you actually eliminate the scattering events or do you just stop the backscatter?
So in the decelerator, you stop the electrons, the idea is you stop the electrons from going through the scintillator. So you capture all of the energy in the scintillator.
You actually stop.
Yeah, so there always is a little bit of backscattering from the scintillator itself, which you can't really capture, but the idea here is that you actually stop the electrons in the scintillator. And in fact, the signal level goes up as you apply the deceleration voltage, because so much of the energy is going through into the substrate. So the signal level goes up as you decrease the net voltage. So the backscattering is not an issue with the decelerator. In the lens-coupled systems, you have a thin scintillator that sits on a very, very thin substrate. And so there's no significant backscattering from that, and then the electrons just go through the substrate into vacuum. I don't know where they end up. Someplace that they don't scatter back up into the scintillator. Or if they do, they're distributed so uniformly they produce a very, very low intensity uniform.
So what I was driving at is those electron events that are ending up as, well, not signal really, they'll be contributing to the signal.
That's right. Yes.
As opposed to just eliminating them as noise.
That's right. But one of the advantages of the decelerator though, is over the lens coupled system. In the lens coupled system, you could in principle have a little bit thicker scintillator to capture more of the electrons, but you wouldn't have it thick enough to capture them all. That would produce too much scattering. So you're still capturing a fraction of the total electron energy.